Okay. So the announcements for today are that there's homework number 2, and it's due October 4th, which is the end of this week. And there's also a midterm number 1, which implies that there's a midterm number 2. And that's happening October 10th. And we will be in CIRS 1250. Any questions about the announcements? Yeah.
Are the midterms going to be more proof heavy or code heavy?
Are the midterms going to be more proof heavy or code heavy? The thing about midterms is that we can't ask you to write a huge amount of code because, well, you don't have a computer. So, yeah. We'll ask you to write code, but it probably won't be very much. Which means it'll probably be really, really tricky. But maybe not. Yeah.
The midterm, like separated by sections, so that's for ours.
Is the midterm going to be separated by sections? And the answer is partially, meaning that this section and the section 103, which is the one in at noon, 12 o'clock, will be in the same place in this room. But Cinda's section will be in a different room.
Separated by structure,
By section. But 2 of the sections can fit in one room, so we're putting them in one room. Yeah. Yep.
Will the content focus a lot more on
Will the content be on homework 1 or will it be more on what we've done in lecture? And the answer is it's going to be on everything that you've done up until approximately October 7th. So, programming assignments, labs, homeworks, lecture, the whole thing. It's part of midterm. Okay. Today we're going to talk about complexity of sorting, the problem complexity of sorting, and also start talking about trees. But first, we have a warm-up to do. So this is to remind you about decision trees. So decision trees, if you remember, they're these things that look like trees. They have nodes in them, like that node, which ask a question about the input. So it asks about one value of the input versus another. And we use decision trees to model a comparison-based algorithms, things that are only obtaining their information about the input by comparing pieces of the input. Those are the types of sorting algorithms that we were talking about before. All the ones that you've seen. Insertion sort, selection sort, merge sort. They're all comparison-based sorting algorithms. And I thought as a warm-up that you might enjoy writing down the decision tree for selection sort. However, as I wrote down the decision tree for selection sort, I found that it wasn't so enjoyable after one branch. So I'm suggesting that you do the yes branch as a warm-up for what comparisons are being made in this version of selection sort. Now, before you start doing this, let me just tell you that the indices that are referenced in the decision tree, like 1 and 0, refer to the original array contents in the input array. You will notice that selection sort swaps elements in the array, but don't let that change the index of the thing that you're talking about. So for example, when it swaps, if it swaps the first element in the array with the last element in the array, and then it compares against the last element in the array, it's actually comparing against the first element in the array. Does that make any sense at all? No? The decision tree only records comparisons. It doesn't record anything about changes in indices. It doesn't record anything about swapping. When you look at the decision tree, you have to know what the decision tree is comparing in the input. And so it always refers to the indices from the original array. Prior to any swaps, any reorganization of the array, the indices those are the indices that it's referring to. you have any other questions about this? You remember these things? How many people are really confused and don't know exactly what to do, or not exactly, but don't know what to do this? Okay, so let's do this for like maybe 2-3 minutes, something like that. Just the yes branch. That's it. And we'll get to the other ones. And you can talk amongst yourselves. If you have questions, ask your neighbor. They will know. Oh, by the way, the root node I did for you. That's the first comparison in selection sort. Oh, and another thing, it's only for inputs of size 3. How many people are done with the yes branch? We'll stop when there are 2 people done with the yes branch. And I've got 1. 2. Okay, we got 2 people done with the yes branch. What is the first node along this path? Well, first of all, where are the comparisons being done in this code? That might be the first thing to figure out. It's in findBin. There are no comparisons between input elements that are being done in the code selection sort, except in the function findBin, and right there. That's it. That's the comparison. The only place in the code where you're comparing 2 elements that are from the input array. And now the first time that you go into this, first time you enter this function, S is set to be the array location A of B. And B is initially called with a value of 0, because it's actually I in the selection sort routine up here. So this value here is 0. And so what this comparison does is it compares I, which is b plus 1 in the first iteration of this loop, with a0. Okay, and then what happens? Well, it depends. If it's a yes, then that triggers this code down here to be executed, which changes the value of s. So now s is no longer a0, it's now a1. So now we know that the next comparison in that loop is going to be something compared to a1. What is the something? a2. It's increments by 1, the index I, and it's a2. Then what happens? Well, we're following the yes branch, so we follow the yes branch, but we need more room, so we go over here. And we get to the end of the loop. We return from find min. And what value do we return? What's the return value if I followed an a1 is less than a0 and a2 is less than a1? What is the return value of find min? What is R? How many people vote for 0? How many people vote for 1? How many people vote for 2? 2 is correct. So the return value is 2. So if I have 0, 1, 2, if I have x and y and z, now coming back from find min, I've returned with index value 2. The swap says swap x and z. So this is after the swap. And then we call it again. We call find min again, but now I has been incremented by 1. And so we know that b is 1 initially. So the first, I guess the second thing that we're going to be comparing is a1. And the first thing is going to be, well, 1 plus 1 is 2, so I is 2. So it's indexing a at location 2. And the thing in location 2 of the array A is x, which was originally in location 0 of array A. And remember, we're indexing according to the original indices. And so this is A0. You guys know this already. It's like you've seen this before. Is this peculiar to you? No. Not at all. I compare A1 and A0, that's at the root. I compare A, you can't even read that, that's a 2. You compare A2 against A1, and then you compare A0 against A1. This is not in any way distressing to you. This is what selection sort does. Do I know the outcome of that comparison before doing it? I do, because I'm in the branch that says A1 is less than A0. So what is the only possible outcome of this comparison? No. We know that no is the answer. This cannot be the answer, because we're in a branch that's already done that comparison. That's kind of wasteful. Does that mean selection sort is wrong? No, it doesn't mean it's wrong, but it means it's doing a comparison when it doesn't need to. And this should make some sense to you, because the way that find min works is it forgets everything about the comparisons that it did before, and it just goes and does all the comparisons again in order to find the minimum in what remains in the array. So it will redo comparisons Like, for example, this comparison between x and y, between a0 and a1. It will redo that comparison if the original a0 got swapped in. It will redo comparisons. So that seems a little bit wasteful. Is there anything else that's interesting about this? Well, here. This is, I believe, selection sort's decision tree. So the red arrows mean this is not possible. Meaning that branch could not be taken in any run through the decision tree. What's interesting about this picture? So you remember, this is the entire execution of selection sort on an input of size 3. All of the possible ways that it could execute, the outcomes of the comparisons, are recorded in this tree. And it records, it can record any comparison-based algorithm. It can record all of the comparisons that are done. And the important part is that the number of comparisons that are performed by the algorithm are the number of comparisons in a path that starts at the root and goes down to a leaf. Those comparisons are only a subset of the instructions that are done by the comparison-based sorting algorithm. It's only the comparisons. It's none of the index, it's none of the swapping, it's none of the loops, it's none of that. It's only the comparisons. So this thing, this decision tree, captures its height, captures a lower bound on the running time for the comparison-based sorting algorithms. This is the height. In this case, the height is 3. So the height is running time. It's actually a lower bound on the running time, so the height is less than or equal to 1. Yep.
Does it include the root node, or does it not include the end? Because technically, there's 4 levels here, because if you count the end, so how do you count, like,
Height is the number of edges on the path from the root to the deepest node in the tree.
the deepest node in?
The deepest node in the tree. The height is the number of edges. Okay, so now the question is, how high do these trees have to be? And what we know is that if the output, which is the leaves down here, if the number of those possible outputs, which are just a rearrangement of the input so that the input is in sorted order, if there aren't enough of them, if there aren't n factorial of them, then there will be some input which can't be sorted, it can't be rearranged into its sorted order because that particular permutation is missing from the leaf, the output leaves. So in this particular case, it just happens that we have one leaf for every possible permutation of 3 elements. It could be that there are multiple leaves in our tree with that property, with multiple leaves with 0, 1, 2, for example. But in this case, we just have 1. But we know that we need at least n factorial leaves in order to get all of the sorted orders to be possible outputs. So if I have a binary tree, like this decision tree, and it has n factorial leaves down at the bottom, which is pretty big, how many levels do I have to go down before I can get to n factorial leaves? If I have a tree that's just branching 2 children each time. So 1 node, and then I branch it 2 nodes, and I branch it 4 nodes, and how long? Log base 2 of n. So, or in this case, log base 2 of n factorial. So the number of leaves is n factorial. So we now know that the height of this tree, the runtime, is at least log of n factorial. Oh, I forgot to ask you a question. Sorry. Let me ask you a question. Is there any property of this tree that's interesting to you? This particular tree? Is there something you notice about this tree? It's different than the tree that we had for insertion sort, for example. It's flat. Like, all the leaves are at the same level. And there's no leaf, like before in the insertion sort, there was a leaf that was up here, and then there were a bunch of leaves that were down here, there was one up here. It's like, here, all the leaves are at the same level. Why is that? It always does the same thing no matter what the outcome of the comparisons are. It always will compare the same number of things that it did in the case when the comparisons came out differently. Because if you think about it, what find min has to do doesn't depend on what's happened before. It just checks every single element in the remaining array to see whether it's the smallest. And it keeps track of the smallest. So it goes through the entire array every single time. First it goes through the whole thing, then it goes through n-1, then it goes through n-2, then it goes through n-3. And that manifests itself in this tree by every single path in the tree that goes to an output leaf has length the same. It's always the same height, the same depth to a leaf. Which also shows up when we looked at the best case performance of selection sort. The best case performance of selection sort is equal to the worst case performance because all of the performances for every single leaf in this tree are the same. And it's always n squared for selection sort. But in any case, that's interesting about this tree. Okay, so now we know that the height of the decision tree is at least this, which means the number of comparisons that are performed is at least log of n factorial. So we get this punchline that says any comparison-based sorting algorithm has a running time which is greater than or equal to some constant times n log n. This is cool. I mean, this is not like we didn't have to invent all of the algorithms for sorting in order to make this claim. Right? This is the thing that we were worried about when we were trying to argue that we never have to work on sorting algorithms again. We came up with the best sorting algorithm, merge sort, asymptotically best. We don't ever have to work on any sorting algorithms again. We can retire because we know that there's no faster sorting algorithm. But we didn't have to enumerate all the algorithms. We didn't have to look at all of them. What we had to do was come up with a property that all correct sorting algorithms have, which is that the number of leaves in their decision tree is at least n factorial. And that property was enough to say that sorting algorithms have to have running time, which is big omega. If they're correct, they have to have running time, which is big omega of n log n. Isn't this cool? I mean, if you don't find this cool, then I don't know. And then there's trouble here. Because I think of this as being like the kind of the science part of computer science. Now, this is like the analysis part. This is like the figuring out. If you didn't know this, you could certainly be confused when your boss asked you to come up with a faster sorting algorithm. Or you wouldn't have any tools to say that a particular algorithm you design is the best algorithm for doing the job. These decision trees don't just work for sorting, they work for other comparison-based things like finding the max or finding the min, finding the second max, finding all these things. They have decision tree proofs of optimality. But I also have to tell you the truth. It's kind of rare to understand a problem as well as we understand sorting. That doesn't happen for many problems. There are problems, for example, in which we don't even know. We have algorithms that can run in exponential time, but we don't even have a proof that there's not an algorithm that can't run in, let's say, n to the fifth time, polynomial time. There's a huge gap for many, many, many algorithms. So this is a good one we can understand really well. Anybody got any question about this? feel like jumping up and down because this is a good thing to be able to do. We'll see this again, this idea of complexity, trying to analyze how hard it is to solve a problem inherently. We aren't talking about the programming language you're using, we're just talking about the power of the computer. That's all. Okay, so there's one little niggling detail here, which nobody asked about, which is perfectly fine. Except that, how did we go from here to there? How do we know that log of n factorial is n log n? I know, you're curious. That's why we're going to do an asymptotic example. So, and because I'm really nice, I'm going to do the big O notation. We don't need the big O notation. All we need is big omega. We just need to show that log of n factorial is big omega. So this is just, think of this as just being kind of a warm-up. But we'll just do it. And then then you'll do the hard part. So T of n is log of n factorial. And what do I know about log of n factorial? I don't know much. But I know n factorial is n times n minus 1 times n minus 2 times n minus 3 times n minus 4, right? So that's certainly less than n times n times n times n times n times n, right? So this is certainly less than or equal to log, because log is an increasing function, n to the n. Because n to the n is bigger than n factorial. What is log of n to the n? Oh wow, we're done. Well, that's cool. This is true. Well, it's true for all values of n, but we could certainly, if we want to avoid things like n is 0, this is true for n greater than or equal to 1. And now we have this n log n, and n log n is, of course, now we have t of n is less than or equal to some constant c, which is equal to 1, times n log n for all n greater than or equal to 1. And so we know from the definition of big O that t of n is big O of n log n. And I can write log n here because the base of the logarithm doesn't affect the function by more than a constant factor. It can change from log base 10 to log base 2 without incurring any more than a constant factor change. Yay. That was the warm-up. Now for you. T of n is still equal to log of n factorial. But now you want to show that this is greater than or equal to some constant times n log n. And let me give you a hint. This is equal to, well, what is it equal to? It's equal to log of n times n minus 1 down to 1, the product of those things. And the log of a product is sum of the logs. So this is equal to the sum of log I from I equals 1 to n. So far this is nothing you didn't know already. But this is the hint. The hint is, if I look at this sum, I want to show that this sum is greater than or equal to some constant times n log n, right? I want to show that it's big. It is not true that all of the terms in this sum are big. Log of 1 is 0. So there are many terms in this sum that are small. But, here's the hint, there are many terms in this sum that are big. There you go. I'll give you 2 minutes. Maybe I'll give you 1 minute. And you can talk to each other. It's too quiet. Okay, how are you doing? Okay. So, which ones of these terms in this summation are big, and how would I use that fact to show that this is larger than something like n log n? I know that lots of them are not big. Like 1, 2, 3, but there's a huge number of them in this summation. There's log n all the way down to log 1. And so how many of these are, relatively speaking, big? It depends on what I mean by relatively speaking. But certainly, at least half of them are bigger than what? This is certainly greater than or equal to the sum of log of n over 2 for I equal n over 2 up to n. If I just look at this summation, and I only look at the parts of it for which I is bigger than n over 2, then every single one of those terms is bigger than log of n over 2. Now, you're thinking I'm throwing away a lot here. Right? Like I threw away half of the summation. I threw away all the terms that involve 1 through n over 2 minus 1. I'm only keeping these. How much is this? Is it because it's Monday? Or you just want to be quiet? This is a constant. Log of n over 2 is a constant within this summation. It doesn't change. It doesn't depend on I. So it's something like, I mean, maybe it's n over 2 plus 1, but it's pretty much something like, let's just say it's greater than or equal to n over 2 times log n over 2. We're almost there. N over 2 log n over 2 looks an awful lot like n log n. What is log of n over 2? Log of n minus log of 2. What's log of 2? It is. That's LG. It's base 2. So this is equal to n over 2 times log minus 1. So now what we have is we have something which is equal to n over 2 log n minus n over 2. And we would be really happy if that minus n over 2 was gone. Because we want to show that this is greater than or equal to some constant times log n, times n log n. And right now it's greater than or equal to some constant, 1/2, times n log n, but there's that minus n over 2. So it's not really greater than 1/2 n log n. So what can we do? What can we do? Somehow, this minus n over 2, I want to think about that as being small relative to n log n. But somehow, the n log n part of this thing, the positive part of this, overwhelms the minus n over 2. It pays for that. It accounts for it. And still has enough left over to still be bigger than some constant times n log n. So what you can do is think about using part of the n log n to pay for the n over 2. Another way to do that, or another way to think about it, is that you could imagine splitting this into two pieces. There's an n over 4 log n plus an n over 4 log n. That's the n over 2 log n. I just split it into two for no good reason. Minus n over 2. And if I could show you that this part, the plus n over 4 log n minus n over 2, if that's bigger than 0, we're done. Because then t of n is greater than or equal to 1/4 n log n. Right? I've taken a quarter, I've taken half of n over 2 log n. I've taken a quarter of n log n, and I'm using that to pay for the minus n over 2. Is it true that n over 4 log n minus n over 2 is greater than 0? No, it's not true, because if you try n equals 1, no, it doesn't work. N equals 2, no, it doesn't work. Yeah. 4. As long as n is larger than 4, log n is bigger than 2. N is bigger than 4, log n is bigger than 2. So if log n here is bigger than 2, then n over 4 times log n is bigger than n over 2. So for this is greater than or equal to just 1 of the n over 4 log n plus 0 for n greater than or equal to 4. I put the 0 there just to emphasize the fact that this part is the part that we're really concerned about with. This circled thing is the thing we want to show as positive. Since log n is greater than 2 for n greater than or equal to 4. And now we're done. Because now we know that t of n is greater than or equal to 1/4 n log n, as long as n is bigger than 4. If you want, the constants here are 1/4, and n0 is 4. It's okay? Yeah.
What is that? N over 2 log n minus n over 2.
This one.
Yeah. Can we go straight from there to, okay, because can we just say that isomptotically that the minus half n goes away of the function of the half n log n?
How do you know that goes away?
It's like relative to n log n.
It's true, but why? You know that because this. You know that because log n gets to be larger than a constant for any time. So you can't just say it. I mean, you can, but you won't get full marks, at least in this course. I mean, this is when you're first learning how to do these sorts of asymptotic analysis type stuff. You have to be complete. Are there any other questions about this derivation? Yeah. Oh, I skipped a step. I mean, the other thing you could do is you could say this is greater than or equal to the sum from I equals n over 2 to n of log I, right, because I'm just dropping terms from the summation. And then I could say, well, for every I that's greater than n over 2, log of I is greater than log of n over 2. Right, because I is, the smallest I is n over 2. Think of it like this. I've got these things, and each one of them is log I. And if I look at the ones for which I is bigger than n over 2, they're all going to be bigger than that smallest, that log of n over 2. It's interesting. It's interesting to see what people are. Are there any other questions about this? Yeah.
From the solution of I equals n over 2 to n over 2 times log.
How did I do that? Go up a little bit higher because I can't come. How many terms are there in that summation?
N over 2.
About. It's actually n over 2 plus 1. But sure, n over 2. And so I have n over 2 terms, and each one of them is of size log of n over 2. I have a sum which is at least n over 2 log n. I'm adding up the same thing. So it's just the number of times I'm adding that thing up times the thing. Okay? All right. We're done with that. But it's good to do that. Now we're talking about trees. Holy cow. Okay, we're going to talk very quickly about trees. So trees. Trees show up everywhere. There are family trees. There are organizational charts. There's like all sorts of interesting things you can do about classification trees. Like, do you know what keys are? Like, this is a thing that you take out into the field with you when you're mushroom hunting. And you bring this along with you, and it has questions. And the first question that it asks you is your mushroom got a red top? And you say, yes. You follow page 3. Page 3 says, do not eat. Then, if it's not got a red top, you read the next question on page 2, and it says, does it have a dome top with bumps on it? And you say, yes. Go to page 5. Do not eat. So it's like that. It's like a thing where you do these binary questions. It's a decision tree. It's exactly a decision tree. So those are keys, biological keys that are used to classify stuff. They don't just classify them into poisonous or not poisonous. They also use them to classify them into species. Like if you take a leaf off of a tree, you ask questions about its format, and you get to the species that the leaf came from. I don't know why I was talking about it. But anyway, it's interesting. The other thing in computer science, trees show up a lot because, for example, the directory structure, the file structure that you have in Unix and Windows and everything else, you have a root directory, you have subdirectories off that root directory. Each of those subdirectories has subdirectories. It's just a big tree. Finally, there's call graphs. If you have a call graph in which there's no recursion, so there's no function that calls itself, then that call graph looks like, this is like which function calls which other function. That's what a call graph is. So you start at some function, main, it calls a bunch of functions, each one of those calls a bunch of functions. Your compiler builds this thing. When you're compiling your code, it builds a call graph, so it can do optimizations on that call graph. Anyway, trees show up everywhere. And oh yeah, that's right, we have a quiz. Excellent. This is fun. Okay, everybody, this is crowd participation. The faster we can do this, the faster this slide will be over. And we can go to something actually interesting. Because you know all of this. What is the root of this tree? Thank you. What is the leaf of this tree? Everything down at the bottom. E, E, F. What do we have? I, J, K, L, all the way down. Child of G? Why not C? I agree with you, 100%. But why not C? My grandpa's not my dad. Okay. There's a direction on these arrows. And there's a root. This is a rooted tree. It has a special node which you identified as being the root because of those arrows, because of those directions. This is not all trees are rooted. There are free trees that are free to roam where they wish. I don't know what they do, but they're free. They don't have a root. They're just trees. They just have no cycles in them. And we'll talk about those later. For the purposes of the data structures that we're going to talk about, we will stick with rooted trees because rooted trees for a data structure are good. They give you a handle where you can start. Give you a handle, a root, where you can hold on to it and do traversals from it, etc., etc. But they don't have to be rooted, but they are. All right, so H and I are the children of... What about the parent of E? B. The sibling of D? E and F. You're stopping me if you get confused. The ancestors of K. A, C, G, H. Okay? Who knows? Maybe. Probably not. If you're confused and you want to be precise, what do you say? Proper ancestor. Proper ancestor excludes the node itself, for sure. Proper ancestor. Descendant of G, there are lots of them. H, I, all the way down to N. And the subtree rooted at G. So the subtree rooted at G is the subtree of the tree, whose root is G. There you go. Excellent job on the quiz. This is all the words that define what we just did. Let's just see how I defined ancestor. My parent or my parent's ancestor. Good. A lovely recursive definition. All right, depth and height. So we already know what these things are because we've been using them when talking about decision trees. But just to make sure, depth of a node in a tree is the number of edges on the path from the root to that node. So what is the depth of node F? 2. What is the height? Okay, there's two definitions in the next line. There's the height of X and there's the height of the entire tree. And they've been wrapped together in some very confusing way, which I apologize for. But the height of a node is the number of edges on the longest path from that node to a leaf. So what is the height of G? One, two. What is the height of A? What is the height of the tree? Great, you got it. If a tree contains n nodes, how many edges does it have in it? N minus 1. How do you know that? Well, one way to say is that every node in this tree has a parent, except for one, who doesn't. And every one of those parent relationships is an edge, uniquely defines an edge. You could do it that way. Or you could do it by induction. You could say, single node, no edges. When you add another node, it's got to be connected to the tree by one edge, its parent. So every time you add another node, you add one more edge, so it's n minus 1 edges. Okay, next time we're going to talk more about trees.